This morning we're going to see something on the, let's say, integer programming side mixed with a little bit of fixed parameter retractability, which is different than, let's say, the focus of the previous talks and days. So it's my pleasure to introduce Klaus Jansen. He's a professor at the University of Kiel, and he's going to talk to us about integer programming and convolution.
Thanks for the introduction. So this is joint work with my former PhD student, Lars Roveder, who's now in Lausanne, about integer programming and convolution. So the main focus is here, we look at integer linear programs in standard form. And the considered case, what we here looked at, is where the number of constraints in the matrix is a parameter or a fixed constant. And the entries of the matrix are also small, bounded by some parameter delta. So we will see some applications where especially we get such forms. For instance, knapsack problems, scheduling problems on identical and uniform machines, and where also some other, where you try to find some approximation algorithms using some configuration IPs. You usually get such type of integer linear programs, sometimes also a bit more complicated versions. So we had also some papers where you get some n-fold structures. But this is a quite nice, interesting case. So what's known about this case? So maybe I should mention, so the typical thing what people looked at is if the number of variables is constant. So there are algorithms by Lenstra-Cannon where you know they run in a reasonable running time. But if the number of constraints is small, for instance, only one, and you don't have this second restriction, you have already the knapsack problem and you have an NP-hard problem. So that's more difficult here there. So what's known? So there were two algorithms, one by Papadimitriou in the 80s. So we had a running time, an algorithm with a running time where we have m squared. M was the number of constraints in the exponent. And recently this was improved by Eisenbrand and Weismantel using some other techniques, what I also will show you in the talk, where you have here a dependence only of 2m in the exponent times the right-hand side and the number of variables. So what we did is we improved slightly on this. So what you can do is you can avoid the term n here. So you can use it only as preprocessing. And instead of the right-hand side, so the largest value on the right-hand side, you use only a logarithmic of this. And that's also useful what we see later for feasibility and proximity results. Furthermore, so we looked at also, can we improve this further? So what happens if you would like to have something with 2 minus delta here in the exponent? And we were able to show that this is somehow equivalent to finding a subquadratic algorithm for the so-called min-plus convolution problem. So now we'll discuss that also. There's some assumption that you cannot do that in subquadratic time. Otherwise, there's a collection of problems where you get improvements. So that's one thing. The second part is we looked also at the feasibility problem, so where we don't have an objective function. Here it's quite nice, so the exponent gets down to m instead of 2m. And here we have also a lower bound. So if you would try to get something with m minus delta here in the exponent, that would contradict the strong exponential time hypothesis. And I will show you this here also. And this was also studied by Eisenbrand and Weismantel, where they have a similar dependence here. This is the right-hand side without the square. And here we have also the log term. And so the other results I will discuss also later in detail. So we looked at unbounded version of knapsack or subset sum problem, where the parameter is here the maximum weight of the items, and C is the capacity of the knapsack. So if you look at the literature, that were the previous result what you had. Either the capacity goes inside, and that was improved to delta square times n. And unbounded was a bit better. So, and we could avoid somehow the dependence here on C. We could improve this slightly and this also.
Sorry, what is unbounded?
Unbounded means that items you can take several times without a limit. No, that is
The knapsack constraint. It's
Yeah.
just you can take items more than one
But
time.
subset sum is multi-set sum would be.
yeah. You have numbers. You would have you can take numbers several times, but you would have the capacity exactly. Right. And the other application, what also we discussed later, is the scheduling problem where I worked a lot on. So the previous result, what I had is with Versche and Kim Klein is, so we had the epitas. Epitas means where the running time is a function in 1/epsilon plus something that's polynomial in the other parameters. So that was the previous result with the log to the power 4 inside in the exponent. And using these algorithms, what we found is we could improve this also to 2. It's much easier as before. Here n is the number here of jobs and m is the number of machines. Yes?
I guess you have two results. One is the exponent, you made it almost tight, right?
Yeah.
And the other one is the right-hand side dependence. But if the right-hand side is much larger than a poly times delta, then things get periodic or something like that. Is that true? Or
What do you mean? For the problem before?
right?
For which problem?
For general IP with, I mean, the first slide, problem with the first slide.
Yeah. If the right-hand side is quite large, we see that also we had some, there were also some proximity results where you can reduce the right-hand side later on. But avoiding the n term there helps also. Then you see we can also get faster results then, using the proximity afterwards.
The exponent in M is
Yeah. Yeah. That's what we will see later when I will just.
the harder part. The exponent, getting the exponent tight, is that?
You will see. I think so. Yeah. Okay. So what is the main idea? Also already by Eisenbrand and Weissman, that's quite nice. Is the so-called Steinitzlemma that's used heavily here. So you can take any norm here in R to the m, and you have a collection of vectors where the norm of all the vectors is at most 1. And if you sum up all the vectors, you get the 0 vector. Then you can prove that there is a permutation of your vectors so that all partial sums here are bounded by the dimension, by m. And that's quite nice, no? And that was proved by Sebastianov and others. And you can also find a nice proof in the paper by Eisenbrand Weissman. The main idea is the following. Assume that you have a path here that goes from the original back. You can reorder the vectors so that you always are in a box of value m here. And how you can use that? So look at an optimum solution of the IP, x star. Then you say, okay, I take x1 star times the first column, x2 times star the second column, etc. And recall, in our case, all the norms are bounded by delta because it was the largest entry. And it was an optimum solution of this here. What you can do now is you can, if you have now here you have a path from 0 to the right-hand side b, and you can reorder this now so that you get a path that's very close to the diagonal between from 0 to b. So they are not far away from this. Is that what you will use afterwards? Okay, so how you can prove this formally? That's also not so complicated. If you look at the columns of A where your sum is B, that's your optimal solution, then you can find a permutation where the partial sums are close to the diagonal, B divided by T, by a bound 2m delta. And it works as follows. You take these vectors here, Vi minus the right-hand side divided by the number of vectors. And then you have to scale it by 2 delta. Because why? Vi divided by delta is at most 1. And B divided by T by delta is also bounded by 1, so you get the norms of the vectors are 1 in the infinity norm. And then if you plug that in, that comes directly out of this. Huh? Yes?
Repeated copies of each.
Yeah. Yeah, repeated copies. No? So you take your optimum solution here. And then you see directly that this works. So how you can use this now? You look at all the corresponding vectors here that are close to the diagonal, and then you have to compute the longest path here from 0 to b. So an optimum solution is the longest path, a feasible is a path here. The vertices, how many vertices do you have? So we have something like m delta to the m, because we have a vector of dimension m times the largest entry in B. And the number of edges, so how do you get an edge? So we connect two vectors. If the difference is a column here, and the weight gives you the length of the edge here. And then you see directly that you can, with the longest path, you generate here an optimum solution. So the running time is the number of vertices times the edges, therefore you get this. That's the main idea, but there's some other thing what's quite interesting. You can also see that there is an optimum solution where the norm is bounded, because you don't have more than the number of vertices here in your path. And that means the one norm is here bounded by this term. And this is also used later. Okay. How can you improve this? So the idea is somehow that you take your path, and then you look at a position somewhere in the middle after t over 2 times number of vectors. So we take, again here, the columns corresponding to an optimum solution here. And then we know that the first t over 2 vectors together this is optimum for the right-hand side B prime. And the other vectors are optimal for B minus B prime, where B prime is somehow close to the point 1 over B divided by 2. And that follows directly by Steinitzlemma also, that both of the vectors are not too far from here because of the partial sum. No? The partial sum is bounded here by this. And that's what you can use then. So how does it work? So finally, we use a dynamic program to solve the solution. Because of the bound with the optimum solution, let me see that again. So we had the bound here for the one norm of our optimum solution. You can make this a bit larger to go to the next exponent of 2. So you can assume that the norm is 2 to the k, and k is then this log term here. So if you plug this in, you get the value here for the bound of the optimum solution. And if you take the log, this is the number of iterations what we have to use later. No? So and the idea is to go stepwise. You start with norm 1, 2, 4, etc. until you reach your optimum solution. And it's sufficient only to take the smaller solution and connect it later. You can use the other solution again above. So what we solve now is iteratively. So you look at all right-hand side that are close here to the diagonal by these values. It's a bit larger as what we have in the Steinitzlemma. You see later why is that why do you need this? And we solve this problem here with this modified right-hand side, this one norm here. And you see if you plug in, for instance, I equals 0, you get the original problem. And what you do is, for one is also interesting. So if you plug the first iteration for k inside, you get 2 to the 0, this is 1. That means you take only one configuration. It's quite easy. No? This is the initialization here. Then you look for 2, you connect 2 configurations, etc. And that's also where you use the convolution step later. You convolute solutions of 2 ways together. that they form the corresponding values. So why do we use this value here for the bound? So suppose we have one iteration I, we have a right-hand side that's close to the diagonal with value 4m delta. And that means we have a solution here with this right-hand side with these vectors, so with our optimum solution ordered by the Steinitzlemma. And what you do is now you take half of the vectors here and look at B double prime. And then you look how far is B double prime away from the next iteration. So if you have 2i plus 1 in the denominator. And then you can split this in two parts. For the first part, we know by the Steinitzlemma that the difference is 2m delta. And for the other part, by assumption here, we have this distance is 4m delta, but you can scale it with 1 over 2. So in total, we get here also 4m delta. That's the reason why we use this, because then you have if you have solution for this, and also the solution for this here, that you can prove in the similar way, then you get solutions for this above. That's the reason why we have to add the value of 2 here. Okay. So finally, what you do is by the convolution, you guess the value B double prime, and you have only a limited number of candidates for this because they are close to the diagonal. And then you look at the solutions for B double prime in the previous step and for the remaining part also, and then you connect both solutions. So it's a merging of different types. So let us look how the convolution works. So in general, the convolution is defined as follows. You have a sequence of numbers, one sequence R and one sequence S. And you would like to compute the values Ti, where Ti is the maximum of the combinations where the sum of the indices gives here this I value. So that means you connect this value, etc., and take the best overall. And if you look at our case, if m is only 1, we have only one constraint, then this directly corresponds to max plus convolution, where the size here is the number of candidates in this case. And for general m, you can also cast this, you can also do the same, and get a size of the number of candidates what's a bit larger. So then you have not only single elements, but vectors what you have to combine. Okay, and what's known for this, some interesting thing. If you have an algorithm for min plus convolution, that's has a similar running time. Min plus or max plus makes no difference here. What you get is here now the following. So the size here is the number of candidates. So we have this running times the number of iterations what we have, plus some pre-processing at the beginning, where you have to eliminate some double elements. And that gives you the running time for the integer linear program. So what you can do, for instance, so the convolution step can be solved in n squared time or even a bit faster. So one possibility is to plug in n squared divided by log n. And then you get such a running time finally by inserting and calculating this. Okay, that's one thing. So this shows you how we get the running time here.
So n squared is trivial, but this n squared log n requires more.
Yeah. There are some recent papers where people looked at how to improve this slightly.
So so n squared over log n is classical, or it's more?
No, it's also more involved.
Ah, okay.
Yeah. And there's also some further results, slightly better as this. Okay, that's one way, but you can also go the way back. And that is how we can prove a lower bound. There's some, so what we were able to prove is that if you have an algorithm where the running time is 2m minus delta in the exponent here, then you can prove that the min plus convolution can be solved in subquadratic time. And there's some recent papers about how to connect these problems with a collection of other problems. For instance, by Sügen et al. They had an ICAL paper about this. One case was, for instance, that the min-plus convolution is related to the unbounded knapsack problem, where C is the capacity here. Yes?
You just use m equals 1 or more general?
That works also for general M. We see that.
You use higher m for getting the...
I show you how that works. Huh? It's not complicated. No? So this was proved by Sügen et al. What we did is, one thing is you can relate the unbounded knapsack problem directly for m equal 1, and then you can generalize it for larger m values also. Let me show how it works. It's not complicated. So we have unbounded knapsack, so we have a capacity at most C. These are the profit values here. You see, okay, you can take items several times. That means you have here the unbounded limit. And what you simply do is you add some extra variable to get equality constraint. And then if m is 1, and you assume that you have such a running time, you see all the values are delta. The capacity is the right-hand side. So this is O of C. And then if m is 1, you get directly this here. This is not complicated, no? So a bit more interesting is the case if m is larger. So the idea is here to reduce the delta by additional equalities. And that works as follows. You use something like carryover as an idea behind this. So you write here your capacity and your weights, something like dual numbers but with a different basis. So the basis is the new delta value, is the capacity to the m square of this. And then you see all the values here are bounded now, also the capacity parts. And one constraint like this, you can write as a sequence of equalities where you use the carryover here somehow with an extra variable that goes from here to the next constraint, etc. You can prove that both things are equivalent. So the nice thing is now the coefficients are all smaller now as the original coefficients. And
So how big are the coefficients?
the coefficients are now this here.
I see. So
The capacity, mth root of this, yes.
I see.
So then you see that you can do that. Suppose for a fixed m you have an algorithm with such a running time. So our construction shows that we can solve this now. The biggest entry is this here. So and if you plug this in, so delta and the right-hand side are bounded now by this. And so we have one term that depends only on m. You can move this out. And the rest, the m is cancelled out. So you get a function in m times that is a bit slightly better than the capacity. So that works at least if m is a fixed constant. It's a bit more complicated if m is larger, then you don't get directly a contradiction. So that means an unbounded knapsack can be solved in subquadratic time and then also min-plus convolution. So if m is fixed, so you have a fixed number of constraints, there's no chance.
So you're saying Sügen et al. Proved that unbounded knapsack implies min-plus convolution?
Yes. This is by Siegel. There was also another paper that did similar things. Okay, feasibility is a bit easier because the convolution gets simpler, because we have only to check is there a solution. We don't have to look at the best longest path. That means in the convolution you get Boolean values here, or values 0 and 1. You get a Boolean operation here. This is easier to solve. Use Fourier transformation in n log n time. And if you plug this in, you get directly, you see that it goes faster. So the feasibility was this running time, what we had. So instead of m squared, you get an m here then. No? And the rest is only by inserting.
So it's the same algorithm, but with a different convolution operator?
Yes. The difference is the convolution only here. The rest is similar as before. Yeah. Okay. And here you can also prove a lower bound. And what's interesting is there was a paper by Abu and others, I think they published it this year, last year in Soda. And they proved that but the result was known already some time ago. So this is the proof the following for the k-sum problem, the following version. So you have a parameter t and then collection of numbers, k subsets here, where the sum of all the elements is n. And then you ask, is there a possibility to choose an element from each set so that the sum of the values is exactly the value t here. And they proved a very nice result that it helps us a lot. They proved here if the strong ATH holds, then there's no algorithm for k-sum with this running time. So the nice thing is the dependence on t also here, t1 minus delta, and a polynomial in n. And this you can use here directly to prove that there's no algorithm for the feasibility problem, where you get a running time of n to fm, and this here to the power of m minus delta.
And what do you get for n again in yours? I thought it was linear.
So you, sorry?
So what's the...
So this is, so if you would like to improve here this by a little amount, but by some fixed delta here, so you can show that it's not possible even if you take here a very large value, a function in m.
Right, and now what is the function in m for the upper bound? I mean, for your actual feasibility algorithm, what do you get?
This is linear in n.
So it's 1.
It's outside also.
Right, so
Yeah.
fm is 1. And you're saying even
Yeah.
if you allow...
You can even have, the reduction shows you that it's much higher here,
I see.
but it's not important. The important thing is this here, no? That you cannot improve the exponent here further.
So there's
And
no...
that's quite nice. We have a algorithm and also a lower bound for this. No? So I will not go into details, a bit technical, this part, but I will show you something else. Proximity, because it was also done by Eisenbrand and Weismantel, and you can connect this also with our algorithm to improve further. So look at an integer linear program where we know this is at least has a feasible solution and this is bounded. And then you look at an optimum vertex solution of your LP relaxation. And then they were able to prove that there is an optimum solution for the ILP where the difference to the optimum LP solution is bounded by this term. And that helps you also further. Because what you can do is you can reduce the right-hand side, because you know if your IP value is larger than this amount, then you know that this has also some amount on the corresponding variable there. So that means you can see that this value has at least this amount corresponding to the LP value. And if you plug this in, you see as a consequence that you can reduce your right-hand side also. And if you plug this in, they prove then optimality and feasibility can be done in such a running time. So with 4m plus 2 in the exponent and 2m plus 1 here. So you see you avoid here the right-hand side, the b value. So b infinity is here not. If you plug this in, you can avoid this. What nice is we have a log term there, and then it goes even faster. That means using our result, we get such a running time. So you have 2m here plus the running time of the LP. In this case, you get m plus the running time of the LP. And LP is usually faster here. So that's quite nice. So your proximity K you can also use to further reduce your running time. So and now I will come to the applications. So the unbounded knapsack problem. What you can use is here is the feasibility problem is sufficient. Is that right? No, for the unbounded subset sum problem, your feasibility for the other one. The LP is quite easy in both cases. If you look at the fractional knapsack or etc., then you can use it in such a running time. If you know that if you're double elements, you would avoid this. No? So otherwise, you get an n extra here additive. Subset sum is even easier because you can take one element simply. and take it completely with a fractional value. So that goes in constant time. And if you plug this in, you get directly these running times here for both versions. So it's delta square or delta times log n, log square delta for the problems. Yeah. Okay, that's this. And the other result, so I worked a lot on the scheduling problem. So we have jobs here. And there's also somehow where I get into this, because you can see later the ILP, what you get, has specially this form what we have. So we have n jobs, we have m machines, they have some processing times. Here are your jobs. The colored means here somehow the sizes of the jobs. And what you would like to find is a schedule, so assignment of jobs to the machine, where you minimize the maximum load on the machines. And so that means somehow a distribution of your jobs here, and you would like to minimize the make span, the maximum load on here. And so the main idea is the following. So first, there you have some pre-processing steps. At the beginning, you use an approximation algorithm, usually with a constant bound. Then you have an interval where you know where the optimal value is in between. Then you use a binary search over this. And for a fixed value of the make span, you distinguish between large and small jobs. The small jobs you can remove directly. You can add them simply at the end. And for the big jobs, you do some rounding. And the rounding gives you so many job sizes afterwards. So it's a combination of arithmetic and geometric rounding of your job sizes. And then you use the configuration IP. That means you use a variable for each multiset, so a combination of jobs that you can put on one machine with the corresponding make span t. And then you get these IRP. Ni here is the number of jobs of a specific size. M is the number of machines. And then you see the number of variables is quite large. It's exponential in 1/epsilon, so many multisets you could have. But what's nice is the right-hand side is bounded, and also the values here in the CIs here, because each size, if you have only large sizes, you can take only 1/epsilon times. And the largest value here is the number of jobs in the worst case, n. So what we did before is we had a running time like this. And if you use the algorithm here now, that gets much easier and directly. So using some pre-processing that goes also linear time, so we were able to improve this, but this is another story. You get this running time here finally by simply plugging in the results for the feasibility problem. And so you see here, these are the number of candidates. It was for the feasibility problem. This was the number of iterations, plus some pre-processing at the beginning, plus the pre-processing for the scheduling problem. And if you insert this, you get this. What's interesting here is there is also a lower bound for the scheduling problem. So you don't have, if the ETH holds, you don't have an algorithm where you improve this here with 1/epsilon. This is not possible. The only possibility is simply to make maybe the log term a bit smaller. And we have some recent paper that comes out soon where you can also avoid this, make this a bit smaller by having only one log times some log term, but that use some further ideas.
Do you need like something for like SETH or something stronger than SETH?
For the lower bound?
This is like for approximation.
ETH we use there, yeah.
Ah, okay.
Yeah. Yeah. We proved this some time ago with, I had a student from Hangzhou, Lin Chen, and his co-advisor. We were able to prove a lower bound for the scheduling problem, even for the approximation algorithm. That's quite nice. Okay, that's it. So I conclude now. So what we have seen is an improved pseudo-polynomial time algorithm for the number of constraints. So m goes here somehow in the exponent. We have an equivalence to to the min plus convolution problem. We have also a lower bound for the feasibility ILP under the SATH. So you can also use the proximity results to reduce the running time. And we have some application in scheduling problem and also the knapsack problems. And that's also somehow, so my main area is working on the scheduling problem, and I entered somehow by accident here the integer programming part. So there's some open question at the end. This is also mentioned already by Eisenbrand and Weismantel. So if you have a bit more general integer linear program where you have also upper and lower bounds on your variables, then things does not work so easily. So the best algorithm here has still a dependence on m square. And the question is, can you do that even also faster to get here m, or a bit faster as m square? Thanks for your attention. Yes?
So there are some other dynamic programming problems where there's this property called the Munch property. I don't know whether you're Mountain City.
Mm-hmm.
That's somewhat reminiscent of what you're doing for the feasibility question, because you get from n squared down to n log n. Is there such an application?
Yeah, I saw there is a paper where they could solve for a knapsack on some other variants of the problem the convolution step faster. Using, if you can, they could prove that they have some special property there, not directly among, but similar, where the convolution gets even in linear time.
Not even log.
Yeah. There was a paper last year on ICALP where they had such a result. Other questions?
Would there be like other interesting parameters other than delta that you could put on these matrices that would give you faster running time?
Maybe, for instance, you can look at the largest determinant what you have. No? It
Yeah.
should also go faster, yeah.
All right. If there are no more questions, let's thank the speaker again. We have a long break.
Yeah. Oh, with some extra time, yes.